may I ask you to please all rise as we welcome the procession.
Good afternoon. Please be seated. So, as you can see on the program, my name is Wikus van Niekerk. I'm currently the Dean of the Dean of the Faculty of Engineering. But what is very important, I'm also a mechanical engineer. So at least this evening I will understand about half of what Ryno is going to tell us. I want to welcome all of you here, but specifically I want to welcome the DVC Research, Innovation and Postgraduate Studies, Professor Sibusiso Moyo. Thank you very much that you are here, Professor. I also want to acknowledge Professor Corny Schutte, who is our Vice Dean, Research and Industry Liaison, as well as Professor Johan van der Spy, who is the Chair of Mechanical and Mechatronic Engineering, and of course, the man of the day or the afternoon, Professor Ryno Laubscher. Then also Joël Laubscher, Professor Laubscher's wife. Thank you that you are here. Also Eben and Lehana Laubscher, the parents of Professor Laubscher. Thank you very much that you are here, as well as David and Ryno Rotsev, the parents-in-law. So thank you very much that you are also joining us for this occasion. And then I see a number of colleagues from both the faculty, from work. I even see people that I know from other universities like Northwest and UCT, and you are very welcome at Stellenbosch as well here. And then there are a number of other friends and collaborators and students who are here, and also everybody who are attending online. Thank you very much for your online presence here as well. Then I always have a little two notes here. So one, I have to please remind you that we are streaming, so please make sure your cell phones are on silent. People that need the restrooms is out that door to the left, and then on the left-hand side as you go out. It's also on the way to where the reception will be after this event. And then in the case of an emergency, there's an exit there with the stairs going down, but there's also an exit there with stairs going down. So in case that the speaker is so hot and ignites the building, then at least we've got a safe escape from it. So thank you very much for everybody who's here. It's really a pleasure to have you all here, and we always look forward to these inaugural lectures, where, as they always say, a professor now has come and he has to now profess to us, right? So Ryno, you've got to profess. But before we give Ryno the mic, just a short bio of Ryno. So he started his academic journey at Stellenbosch University, where he earned a bachelor's in engineering, mechanical engineering in 2009, which was then followed with a master's in science and engineering. That's still an old degree in 2012 with his master's. He then realized that you need to get some real practical, real-world experience if you want to work effectively and train the upcoming engineers. And he joined John Thompson Boiler and Environmental Solutions as a mechanical engineer, where he actually did quite a number of impressive things. He was involved with component-level numerical modeling, design, plant commissioning, right? So that's actually, those are the real engineers, not we sitting here and making the drawings and all the sums. There where you have to actually now see why the hell it's not working, right? That's real good experience, and then also project and technical management. While he was working, right, so clearly there's a lot of capacity in his day, he was also pursuing his doctoral studies, focusing on computational fluid dynamics, where he was modeling advanced turbulence chemistry interactions using deep learning-based chemical kinetics integration. Don't worry about what that means. He's going to explain that to us a little bit later. And he graduated from Stellenbosch University with a PhD in 2017. Then he also held other positions prior to joining Stellenbosch as a faculty member, including he was part of the software development team of Inexio, which is a German company based in Germany, where they developed utility-scale energy system process modeling, as well as CFD and AI, artificial intelligence models for industrial systems. He also served as Chief Research Officer at ATPROM Research Unit and Energy Efficiency Center, and that is at the University of Cape Town in the Department of Mechanical Engineering. He's now a full professor in the Department of Mechanical and Mechatronic Engineering, and his research focus on the CFD modeling of thermal fluid systems and the application of scientific machine learning techniques. So Ryno, we are looking forward to listening to you profess to us this afternoon, and we are waiting in anticipation. The floor is yours.
Thank you, Professor Nick van der Kerk. It's nice seeing my family today here, where I can lecture to them for a change. They can't interrupt me. They have to listen to what I'm saying. So that's quite a nice change of pace. So the title of my presentation, if you didn't see it in the email, is Harnessing Deep Learning for Thermal Fluid Systems. So this is essentially one of the areas that I do my research in. I'll also cover some of my other areas that I do research in. But I think because artificial intelligence and deep learning is so topical these days, occasion to actually discuss AI and how we as mechanical engineers, or specifically thermodynamicists, use AI in our research. So the table of, or essentially the contents of my presentation, I'm going to quickly cover all my research areas, just one slide for each area. Then we'll look at the application of deep learning in thermal fluid systems. We're going to look at data-driven and scientific machine learning, so that would potentially be a new topic for many of you. We'll also then look at some of the data-driven projects that we finished in our research, and then we'll also look at some projects that we finished in scientific deep learning. And then finally, I think quite a nice case study where we use something called differentiable simulations, specifically on human cardiovascular modeling. So I think typically the audience usually likes hearing biomedical applications, although I don't pursue biomedical applications on a day-to-day basis. Okay. So maybe just some definitions for the non-engineers. What is a thermal fluid system? A thermal fluid system is engineering systems that pertain to simultaneous transport of heat and fluid flow. So a good example that everyone can relate to is, I don't know if you can see the pointer, is a power plant. So a power plant essentially consists of pumps, boilers, turbines, and condensers, which is work machines and heat exchangers. So we have a fluid flowing inside the power plant, typically steam or water. In the boiler, there's heat transfer to the water, it evaporates. The steam that is generated then drives a turbine where we extract work to generate electricity. The low quality steam that leaves the turbine gets condensed in a heat exchanger, and the liquid is then fed back into a pump. So that's a good example of a thermal fluid system that most people can relate to. Now we combine this, in our research, we combine this area with deep learning, which is quite a distinctive field from typical mechanical engineering. And deep learning is a subset of machine learning, specifically where it looks at using artificial neural networks with multiple layers. Shallow learning, or typical machine learning, are techniques like support vector machines and linear regression, or single layer neural networks. So as soon as a neural network, I'll maybe point this side as well, as soon as a neural network has multiple layers, we classify it as a deep learning model. Now, what do we do with these deep learning models? We basically give data to those models, and the model learns to predict patterns. So it learns from the data to predict a pattern, what would be expected if we feed it similar input data as what it was trained on. Now, our example could be, I can feed in a couple of months of weather data into the neural network as scalar values, temperatures, humidity, wind directions, and we can ask the neural network to predict the next day's weather conditions. So that's a nice example of how we could use deep learning. A very simple example. It's going to get a little bit rougher in the lecture compared to that, but that would be an example of a deep learning application. Okay, with that sort of picture in mind, some of my research areas. So one thing what I do is essentially I apply deep learning and AI in these fields. I'm not a pure AI researcher. I don't only do AI research, I apply it to engineering problems. And the specific engineering problems that I research is, first off, is combustion research. In combustion research, in my previous life, especially at UCT and in industry, we did a lot of modeling on solid fuel, so PF being pulverized coal, and biomass combustion in power plants. And typically what we do, we would look at building complex simulations, I'll show this way, this side as well, complex simulation of the combustion of the solid fuel in the boiler, and then model the transport of the solid fuel as it devolatilizes and turns into gas, as it combusts, and as the heat transfer is transferred to the walls, generating steam for a power plant. We would model those simulations using CFD, and then also then, to make sure that these models are accurate, build test rigs. So that would be a test rig that we installed on, I don't think I may say which power plant in South Africa, a power plant in South Africa, where we actually compared our CFD results, which is the dark dashed line or the black dashed line, to measurements on the plant. And you can see with these models being very accurate, we can then use the model to study what would the plant do under upset conditions or if something goes wrong. So if the models can predict what's going to happen, we can use it to inform us on upset conditions or increasing the load of the plant and see how it will perform. Another area that I focus on is microjet combustor development. So that's more in the aerospace, in small-scale power generation space. And you can see a picture there in the middle at the top of the slide where we have a little aerospace gas turbine which is used in UAVs or a little small-scale power generation. We would look at the development of those little combustors because they basically operates quite different to the larger gas turbine combustors. So because of the small scale, there's unique challenges in the development of those small combustors. And then a very topical area that we currently, myself and Professor van der Spey is doing research in, is blending hydrogen into hydrocarbon fuels to ensure that we have a cleaner burning gas leaving the combustor. Because if you burn hydrogen, you essentially only make water. That's not completely true, but I think for this discussion, it is sufficient. So putting more water and taking more of the hydrocarbon fuel out, we get a cleaner burning fuel where the gas that leaves is mostly water, which isn't a harmful pollutant to the environment. And we also do complex CFD simulations. One of my current PhD students and our colleague is looking at how would we model adding more hydrogen into the combustion chamber and how the combustion process will change. We also do power cycle research. Power cycle research essentially is now not focusing on a component, the combustor in the gas turbine, but looking at the entire power system. So that would be in the entire power plant. Not just on a component level, but on adding all the components together and see how the system will respond as the required load changes or the weather conditions change. Now, one of the power cycles we're doing a lot of research on is SCO2, that is supercritical carbon dioxide. Typically, I think the average person would be used to a solid, a liquid, and a gas. Those are your three phases, but there's an additional phase called the supercritical phase that is above the critical pressure of a fluid. Now, above the critical pressure, a supercritical fluid is classified as a fluid that has a density similar to that of a liquid, but the viscosity and thermal specific heat of that of a gas. And that gives us the ability to design power cycles that are extremely small and high power density. To just give an example, in a SCO2 power cycle that we developed for a solar application, you can see a 250 megawatt steam turbine to scale roughly in blue drawn on the presentation slide. To give you an idea what a 300 megawatt SCO2 turbine would look like, it's that little red dot. So to generate more power, 50 megawatts, so that's a lot of houses, the size of the turbine would be substantially smaller, and that's due to these unique fluid properties. One of my also PhD students that's completed, and our colleague, Dr. Rashid Hafaji, in his PhD, he actually looked at how can we take an existing steam power plant, add in supercritical heat exchangers into the boiler, overfire the unit, in other words, putting more fuel in, burning, giving it a larger heat output, and then essentially add on a little supercritical power cycle to the existing Rankine cycle to top up the power output. And we actually showed using CFD and detailed component modeling that it is really a viable option to generate more power from an existing power plant. And then finally, I also look in my group or with my colleagues, we look at research in turbo machinery and mainly microgas turbo machines, again, small scale turbo machines. As you can see, a little test rig of a small scale aerospace jet cycle that we kitted out there in testing. I see the fuel supply can, there's just a water can and it's open, so that's not a very safe picture that we show there in the bottom. So we do tests on that, and of course a lot of work on the SCO2 compressors and turbines for that specific power cycle. So just to give you an idea, for a 16 megawatt SCO2 turbine, which 16 megawatt has quite a few households, that turbine would roughly have an engine height of 25 millimeters, and at the outlet would be 50 millimeters. Tiny components, massive power generation capabilities. But of course there are some challenges because there's no such plant that actually exists yet. We are busy developing it. Okay, those are my areas that I typically do research in. Now we'll cover deep learning applied to thermal fluid systems. So how do we use these deep learning techniques in those research areas? Okay, so let's start off by asking how can we use deep learning in thermal fluids? Now, first thing that we can do is we can build surrogate models. And surrogate models is essentially where we train deep learning neural networks as fast approximators of expensive simulations. And how you can think of it is CFD simulations is one of the techniques that we use to simulate thermal fluid systems. And that boiler simulation with the combustion gas was the example of that. Now, that simulation runs between 4 hours and a couple of days, depending on the size of the simulation. So really slow simulations and very expensive to get out. So what we essentially do is we go and run thousands of those simulations, pre-run them on the high performance computing center. We extract the data set, train a neural network to predict the performance of that power plant based on the simulation data. And then when we need to deploy the model as a virtual sensor or a surrogate model to make a quick prediction, the neural network can almost instantaneously give us a prediction once trained. Another application area is system performance forecasting, and that is essentially we have plant data, historic plant data. If we can think about a heat exchanger, let's say we have 3 years of data on a heat exchanger, of if we put this fluid in at this wind condition, for instance, if it's an atmospheric heat exchanger, if we put this steam flow rate in at this temperature with this wind condition, we get this heat transfer rate, and we have enough data over 3 or 4 years. We can build a model that says if for the last 3 hours this was the performance and this was the weather, this would be the next 3 hours worth of performance. This is what we'll get out expectedly in the next 3 hours. So we can build these forecasting models, similar to trying forecasting stocks. Only problem with stock prices is it's a random walk, and no one has really been able to predict it. Otherwise, I wouldn't be here. I would go and make money, but that's not completely true. I like the teaching aspects. All right, so another exciting area is design space exploration using generative learning, and generative learning, of course, is the technology sitting underneath ChatGPT and Claude. It's a type of learning where the neural network can generate simulations or generate answers. And what we would typically do there is we'd take simulation data or plant data of the shape, and we can think of a little wing there. If you think about an airfoil, we know the flow of the air around the wing. We know the lift and drag that the wing generates. We take that shape along with the thermodynamic performance, and we train a generative model. And one of the models that I typically use is a variational autoencoder. And what we essentially do is we squeeze that shape. If you can think about a wing, and the suction side and the pressure side of the wind, we can represent as a point cloud of hundreds of points. We can essentially squeeze that geometry down to 3 or 4 variables. So into a latent space, the reduced representation of that wing profile and its performance. So if you give enough simulations to this variational autoencoder and we create this latent space of this reduced representation of the simulation, we can ask that neural network now to generate new simulations. So previously, it's not just trying to replicate previous simulations. It's now generating new simulation data because trained it to understand the latent space, the general behavior of fluid flow around a wing. Now, I can apply that also to more complex problems that we'll discuss a little bit later. And then finally, we can build data-driven submodels where we can build, essentially in these CFD simulations, we can't simulate all the detail. It would be too expensive. So we can train the neural networks to capture details that it's not easy to simulate mathematically, and then build these neural networks into these CFD simulations to enhance their accuracy. Okay, did I skip a slide? No, I didn't skip a slide there. Oh, sorry, I'm jumping around. There's a little extra thing, many more. These are by no means the only applications of deep learning in thermal fluids. It's just some of the areas that we work in. Okay, so what is the difference between data-driven and scientific machine learning? Because I talked about it in the beginning of the presentation that we have these areas of machine learning that we work in. Data-driven essentially is where we use experimental data or simulation data to train these models. And the training means mapping the inputs to the outputs. The inputs would be, for that heat exchanger example, the flow rate of steam, or the inlet flow rate the inlet flow rate of steam and the inlet temperature of steam, and the output would be the heat transfer rate. So we give those two inputs and outputs to the neural network, and it learns to match the inputs to the outputs. It learns that pattern to predict that pattern. Now, once trained, as I mentioned, these deep learning models are significantly less computationally expensive compared to traditional simulations. Not hours, fractions of a second, but once trained. And that training is still very expensive because we have to generate all the data and then also train the model. And I mentioned you can either take the simulations from measurements the data from measurements or simulations. Some of the limitations is we need excessive amounts of data for the neural network to properly detect that pattern. So we need to run thousands of simulations or have hundreds of thousands of data points. So it needs to see this input-output combination thousands of millions of times before it can detect the pattern. So we need a lot of data. And that is usually a big problem in thermal fluids because we can't measure every detail. It's too complex, or it's too a harsh environment, especially in a combustion chamber, temperatures of 2000 degrees Celsius, high velocities. So we can't really measure there. And now we also need a lot of data. So the other problem is also that the simulations, as I mentioned, takes hours or days to generate. It's also very expensive to train these models, even if they're trained on simulation data. And maybe one of the biggest problems is there's no physical consistency in these models. And what this means is we're only showing it examples of what it should learn, only the input-outputs. It's not learning the fundamental physics. So it has no idea of energy in must be equal to energy out. Mass in must be equal to mass out. So it can break the physical laws if it's overfitted while training. And for that reason, these models have to be very carefully developed so that it doesn't overfit, which means it's breaking the laws of physics when it's making predictions. The other main problem is it's quite bad at extrapolating, making predictions outside the scope of the data that is trained on. So again, in that heat exchanger problem, let's say we're training it for inlet temperatures between 100 and 200 degrees Celsius. If I give it temperatures at 250 degrees Celsius, it will most likely make a massive prediction error. Why? Because it's never seen that example before. So we need to give it the full scope of the examples so that it doesn't create these prediction errors when it makes, when we deploy it as a virtual sensor or as a surrogate model. And maybe just to visualize it, what would it look like? We could have a steam power plant that generates a lot of data for us. So this data is actually the megawatts that this power plant generated. So it's not a simulation, this is a real power plant's data. That's just a diagram of the power plant schematic, or schematic of the power plant's layout. So we have this data, we feed this data into a neural network model, we train it with thousands of data points, and we deploy the model to make predictions. And in this case, the red dots would be the real data, and the black line would be the prediction. So that model was very accurate, but we'll go more into that a little bit later. Okay. So the question is, how can we leverage scientific knowledge in the development of deep learning models? So how can we incorporate scientific laws that scientists and physicists have developed over hundreds of years into the training process of these neural networks? Because a neural network doesn't need to learn Newton's law of gravity or the first law of thermodynamics. We know what that law looks like. We have the equations, we have the physics. So is there a way that we can incorporate those laws, those physical equations that we already have, that are very good models of nature? Can we incorporate that into the learning process? Essentially, mixing data with models, the model equations, to form better predictions. Because the more physics we incorporate during the training of these neural networks, the less data we need. And especially in thermal fluids, as I mentioned, where it's difficult and very expensive to make these measurements, this is invaluable. And this is where the area of scientific deep learning comes in. We mix data and we mix known physics. in the training process. Right, so in scientific deep learning, there are essentially two main concepts, and I got stuck a little bit on the first slide, so I'm going to go a little bit quicker through these slides. The two main applications for scientific machine learning, or ways we can do it, is we can integrate neural networks into physics equations, which is the first example. And unfortunately, there's no chemical engineers today here, I think. I didn't see any chemical engineer. Oh, there's one. Yeah, there's a chemical engineer. We, as mechanical engineers, can also do chemical engineering, I just want to say. So the example that I took here is, the question is, can we integrate neural networks into solving the physics of a mechanical or chemical engineering problem? And the example that I took here is, let's assume we have a constant pressure fixed mass reactor. A good example of this would be the combustion in your internal combustion engine while the piston is expanding. That would be a sort of a constant pressure fixed mass reactor. So if we have a fixed mass reactor that is reacting, there's a combustion taking place, it is expanding, it's heating up, and we're burning out the fuel, shown by the data on the right-hand side. So the dot at the top would just be the temperature over time, that would be the volume expansion over time, and this would be how the methane and the oxygen and the carbon monoxide burns out over time. So the question is, if there are phenomena in that combustion process that we can't capture because we don't have the equations for it, can we learn it from the data to adjust our simulation so that it is more accurate? So the first school of thought, and this is the traditional way that everyone would apply neural networks, I would say in the last 10 years, is we will build our physical equation model, which is just our conservation of species and our conservation of energy, and we will go and simulate this fixed mass reactor, and what you'll find is, if we can take this as an example, the dots for the temperature would be the experimental data, and the solid line would be the simulation output. And you can see that the simulation output under-predicts the temperature. So there's something that we're missing with our model. So how do we fix it? How do we discover that missing bit? So one way that people are, as I mentioned, sorry, not people, researchers, we are not people, we have been fixing this problem is they simulate the model, they look at the difference, and they train the neural network to predict that difference, and then they correct the model with that error, with that residual. But the problem is, any control engineer would tell you what you're actually doing there is derivative control. And derivative control is suspect or susceptible to drift. So as your neural network makes a prediction error, it can't autocorrect and it will start drifting away from the real answer. So a better way would be to do integral control. But integral control is very difficult once the simulation has already been integrated, solved it. And that's where scientific deep learning comes in. Because what we would like to do is we would actually like to know how is that chemical reaction rate, that omega dot, how is that actually different from the vanilla simulation that we ran? Where's the missing physics? Because it's most likely in the mixing rate, which is that omega. So what we can do is plug a neural network in there. Inside the simulation, integrate the simulation by solving a neural network inside the simulation, and then do backwards differentiation through the integration, which sounds crazy, but we are actually able to do that. So through the Euler time stepping, as we simulate the problem, we can track the gradients by doing differentiation through the simulation and actually find the gradients of the error with respect to the neural network parameters and drive that so that the simulation matches the data, thereby learning the missing physics that we couldn't capture. Now, the missing physics could either be, the data that we use could either be taken from an experiment or CFD simulations, and then distilled down to a simpler model that can solve in the matter of seconds or fractions of a second. Another way we can apply scientific deep learning is now not incorporating neural networks into simulations, but incorporating simulation equations into neural networks. And the way we do that is with something called a PIN, or physics-informed neural networks. And essentially what we do now is we don't show the neural network data, we show it equations. And say, learn the equations. Learn that everywhere in the simulation space where we're solving this problem, you must satisfy the physics equations. So if we have a little example, 2D example, where you have dry air flowing in, we have moisture flowing in from bottom to top, the dry air is mixing with the moisture and the humid air would leave from left to right. The question is, can we simulate this flow field, seeing the temperature profile as well as the change in species composition? And what we essentially do is we take coordinates in this domain, feed it into the physically informed neural network. The neural network then predicts the velocities, pressures, and temperatures, and we find then the gradients of those predictions with respect to the coordinates. So if you think about the conservation of momentum, there's a term that we need, the dudx term, the x gradient of the x velocity. So we would feed in a coordinate, let's say the coordinate is somewhere there in the domain, we feed it into the neural network, it makes a prediction on the velocity. Now of course, once we initialize the neural network, that would be complete garbage because the neural network hasn't learned anything. But then we actually take that prediction and tell the neural network, because that's a transfer function, find me the gradient of the velocity with respect to x, and drive that along with all the gradient terms to 0. And if it does that enough, it's actually learned the strong form solution to the physics, to the Navier-Stokes equation. But I'll explain that a little bit more later on. So let's look at something that's a little bit more interesting, which is just examples of projects that we've finished, specifically first data-driven examples. So in this project, we had a client that produces electricity in South Africa. There is only one. I may not name the unnamed. So we have a client that has a power plant in South Africa that's generating electricity. In this power cycle, there's a condenser. The condenser is what's used to cool the steam coming out of the turbine before it's sent back to the pump, go back into the boiler, back into the turbine. The lower you can get that condensation pressure, the more power the power plant generates. I'm not going to go into all the details about that. But that back pressure is a significant function of the weather of the plant. So as you can see that structure there, there's that horizontal black structure, it's all the condenser heat exchangers. So the air gets sucked in underneath the heat exchanger through fans and it blows out. But of course, if the wind blows, the amount of air that we can squeeze into that heat exchanger drops and the back pressure rises and the power output goes down. So in this project, we had about, I think, 3 years of worth of data on the back pressure and the plant performance. And we trained a neural network to forecast the upcoming 4 hours of back pressure so that our client could actually use that to predict this is the back pressure, so this is the amount of power my plant can generate, so that they can inform the system controller of is there a load loss or not on the plant. Will we be able to generate all the megawatts in the next 4 hours? I'm not going to go into all the details now, but essentially got a model that was 82% accurate. And if you just look at the predictions, and I think this is very interesting, we trained it with 3 tranches of data. Initially, the red dots is the back pressure that it needs to predict in kilopascals. And so that's the real back pressure, and the prediction is the blue line. But we trained this neural network only on the power output of the plant, where we said, if you've been producing 100 megawatts in the last hour, what would the back pressure be for the next 4 hours? And we can see the model is unable to capture the pattern. There's not enough information in just the power output of the plant. And the uncertainty, because the model that we trained here is aware of its own uncertainty, so it will essentially say the back pressure is 20 kPa, and I'm 90% sure that's the right answer. So the AI was aware of its prediction accuracy. And it was unable just on the power generation load to predict it. But as soon as we added weather data, suddenly it could capture all the trends, showing that the weather had a massive effect. And then finally we add additional plant values like pressures and temperatures to it, and the model could actually very accurately predict the back pressures 4 hours in advance. Another nice project that one of my PhD students completed, also for a client that generates electricity in South Africa, is can we build a model, a surrogate model, a model that can predict instantaneously the heat uptake in a boiler furnace that's about 150 meters tall, so a massive component. And what we did is we produced 1,000 CFD simulations that took months to generate, and trained a neural network model to predict the heat flux in each one of those vertical segments, also on the heat exchangers, and also that leaves the heat exchangers. And this surrogate model could then be used to investigate as the water in the coal becomes more and more and more, how would the heat uptake in the furnace go down? Or if we switch off the burners at the top row, how would the heat flux distribution change? And how would that affect the plant's power output? We then took this surrogate model and built it into a process model and used it to then forecast and predict what would the plant do at upset conditions, essentially. So we took the simulation that takes about 8 hours, got it down to almost instantaneously so that the client can see, if I now put this type of coal in, this is how my plant will change. If I change these burner flow rates, this is how the plant's performance will change. And what we essentially did is we also then had experimental data. So it's important to understand the simulation data was the only data used to train the model. Then we took experimental data, we took the plant, that model that we developed, and compared it to a real power plant to see how the model would predict the real power plant's performance. And if you look at all the heat exchanges, the turquoise bar is the measured data, and the red bar is the model's predictions. So using just simulation data in the neural network and a lot of CFD data, we can build a model that is a process model and a surrogate model and can really predict the entire boiler plant's prediction at various loads and various fuel conditions. So another project that we worked on is generative learning, where we wanted to build a generative model of CFD simulations. Again, we ran 1,000 CFD simulations. Sorry, in the previous one I said 1,000. This one is 1,000 simulations. The previous one was just 180, but it still took months to solve. And what we did here is we used a generative learning model to try and predict the distribution of a flame. So we ran a bunch of CFD simulations, trained a generative model, and the generative model could then be used to generate new flame profiles. And we wanted to use this model as a virtual sensor that can be deployed with a control system so that the user can actually visualize the flame in real time based on the input conditions into the combustor. This model is quite a complex structure, so I won't go into much detail. But the main thing is that we could predict the accuracy roughly about 1% to 2% compared to the simulation results after the generative model has been trained. And what you can see is, so this would be the original data, the real data, and that would be what the surrogate model, after it has been trained and used to generate new simulation results compared to data that we didn't show it while it was trained. So this data point, it has never seen that data point before, but you could really see that it could capture the actual simulation results. So up to some science, let's go look at some scientific results. There's, I think, 1 or 2 projects left, then I'm done. We'll first now look at the first example of physics-informed neural networks, where I said physics-informed neural networks essentially is used to solve the physical equations directly. So what we essentially do in this case, we looked at 2 heat exchangers sitting in series. We flowed close. Sorry, my English is now running at its end. So we transported cold air over the heat exchangers. The warm tubes then heated the air, and we asked ourselves a question: can a neural network, by just looking at the equations, solve that problem? So no data, just equations. And what we do is we trained a neural network to take in the coordinates in that domain, make predictions for the pressure, the viscous stresses, and the heat fluxes, and based on those conditions, construct the actual balance equations. This is the only math, I promise. Construct the balance equations, and then drive the balance equations down to 0 through the training process, and thereby learning the solution of the Navier-Stokes. So just to give you an example, the neural network will take in a coordinate, an x and y coordinate, and it will then predict the velocities, the u's, the v's, and the sigmas. Because the neural network is a transfer function, we can then get the gradient of the output, the velocities, pressures, etc., through the neural network with respect to the spatial coordinates, and then construct the balance equations. If we drive that balance equation, if we train the neural network to make sure that if you add all those terms together, and it gives us 0, then we've solved the Navier-Stokes equation without discretizing the domain. So we've solved the Navier-Stokes in the strong form, which up to this point wasn't possible. We were only possible to solve the Navier-Stokes in the weak form. So the pins enable us to actually solve Navier-Stokes in the strong form. Now, before anyone gets excited, we didn't win the Millennium Prize, so that's $1 million. It's still not a pure analytical solution. It is a strong form numerical solution. But I believe that this technology will give us the opportunity to understand and unlock a lot of value in simulating complex thermofluid systems. And just to show you how well the physics-informed neural network can solve the problem, so the left-hand column is the pins prediction, and the right-hand column is what the state-of-the-art CFD would give us. So nearly exactly the simulation results that we can get with the pin compared to the CFD. But what we can also do now is we can also then sample in a third dimension. So of course our problem, I'm just going to quickly jump back, has an X and a Y coordinate, but we can also now sample into a third dimension, which is the time dimension. Sample a bunch of points out of that three-dimensional space and drive all that data through the physics-informed neural network, making predictions for each spatial position and temporal position at the same time and solve all those points in parallel on one GPU. So that means we can actually solve forward in time at the current time with one GPU, thereby not just only stepping through time to solve the simulation, but going into the future and solving that condition simultaneously with the current time step. We can then also sample in a fifth dimension, which would be increasing diameters of the tube or larger dimensions of the tube, and just sample in those higher dimensional spaces, thereby solving multiple possible combinations of the problem simultaneously on one GPU, potentially driving down simulation cost of surrogate models from weeks to days. I'm going to skip that one, and I'll quickly talk about this one. So I think this is one of our projects that's getting a lot of traction currently in literature. Is we developed a segregated physics-informed neural network, sort of a new novel concept that we developed, where we said, can we solve this problem with very complex physics, so multi-phase transfer, heat transfer, mass transfer, and momentum transfer. And what we found, if we apply the standard pin to that problem where we're trying to solve all these physics, the model was unable to solve it. So we developed something called a segregated pin, where each pin is solving a portion of the physics. One pin solves the momentum transfer, one pin solves the energy transfer, one pin solves the species transfer. And what we actually found is we could drive the error of the pin down by 62% and solve this problem with a physics-informed neural network. So the pin is very complex, but I actually just want to shift your focus on the results. If you look at the pin 1, which is the standard pin, specifically if we look at the velocity, the temperature, and the mass fraction of oxygen, you compare it with the values at the top of each column, of each little three high column, we can see it's unable to predict the original data, the original simulation results. But the pin 3, which is the segregated model, can accurately capture the physics. What it also, which is very encouraging to see, is that the single pin can't maintain mass conservation. But as soon as we created the segregated pin, it enabled us to conserve mass and not go outside the bounds of physics. Again, I think a very valuable and the first time that someone could actually solve a problem like this. Last example, then we are done, I promise you. And I think this is the one that most, people enjoy looking at, which is it's a cardiovascular problem. It's also just a flow system, it's pipes, it's blood flow, it's nothing else than a thermal fluid system minus the thermal, although your blood is sitting at a temperature. So here was the problem that the cardiologist posed to us. To understand how healthy a patient's heart is, they need to understand what the left ventricular elastance of the heart is. And the left ventricular elastance of the heart is the pumping power of the heart chamber, especially your left ventricle. So how much pressure can that heart chamber generate as the volume changes? What they do is essentially to determine this, and it's a very invasive experiment, is they draw something called a PV loop, how the pressure and volume in your heart chamber changes over time. And what they essentially want from this PV loop is this gradient of that line. And that's called the contractility of your heart. If your contractility of your heart is very low, your heart is very weak. and if they fix your heart valve, in a sense, if your heart valve can't fully close, and they fix it and it can fully close, but your heart is too weak, it won't be able to push the blood through your different organs anymore. So they need to know what the contractility of the heart is to understand how the heart has deteriorated under stenosis. And stenosis is typically if your heart valve can't fully close or fully open. So the challenge was, can we predict that contractility non-invasively using deep learning or scientific deep learning? And what we essentially did is we built a cardiovascular simulation model that consists of the systemic and pulmonary loop of your venous system and your systemic system. So your left ventricle, the blood going to the organs, all the blood's being collected back to your lungs, back into your heart, and so the circulation continues. So we built a little one-dimensional, zero-dimensional model of the cardiovascular system, where each one of the artery systems is represented by two differential equations, and the pressure in the heart is modeled using this transfer function. So the question is, can we determine the pressure in the heart with only taking the blood pressure and scanning the volume flow rate that's going through your heart chamber? So doing an echo Doppler of your heart chamber, looking at the blood flow going through your valves and taking your blood pressure, rather than, which is the current way they do it, sticking a needle in your heart, catheterize your heart, which is invasive, not super dangerous, but very invasive, very expensive, and it's not without risks. So the question was, can we determine that pressure without going invasively into the human's body? So the first thing that we did is we built this model, and we asked ourselves, what are the main parameters that influences the pressure in the left ventricle? So what we did is we essentially did differentiation through the model to find the gradients of each one of the model's parameters with respect to the pressure. And we can see that the main parameters that have the biggest influence, which would be the bars that are going vertically upward, not down, would be your heart's elastance, one of the parameters that they want to determine, so that's obvious, but also the capacitance of your artery system, so the amount of blood that pools in your arteries while your cardiovascular system is running. So what we essentially then did is we knew that those parameters, if we can find them for the human's cardiovascular system non-invasively, we would be able to determine what the pressure is in the ventricle non-invasively. And the way we did this is, if I just walk you through this flow diagram, is we start our model, we take all those parameters that have a significant influence on the pressure in the ventricle, and we initialize them to the standard literature values. Now, if I use the standard literature values and I model my cardiovascular system, I won't get an accurate answer because I'm a unique human with my own height, size of my heart chamber, size of my venous system, of my aorta, etc. So the standard literature values won't give us accurate answers for a specific patient's performance of its cardiovascular system. But we start and we initialize that simulation model with standard parameters. Then we run the simulation and we get our volume flow rate and our blood pressure out. And we compare those results to measurements, actual measurements on the patient. And we ask ourselves, what is the error between what we simulated and what we measured? And what we then do is we actually take that error, we call it the cost function, and we calculate the gradient of the cost function with respect to each of those parameters, and then optimize the simulation using automatic differentiation, which is a deep learning technique, to drive the simulation outputs so that it's exactly the same as the measurements on the patient. Thereby, hopefully, finding the pressure inside the patient's heart, and thereby discovering the elastance. So let's see how it would actually perform. So in these graphs at the bottom right, the right-hand graphs would be the volume flow rate of blood that's going through the patient's heart valves. So you can scan that with the echo Doppler, and we can see the milliliters per second flowing over a beat cycle of the patient. So that's data we give the model. The other data that we give the model on the graph just to the left of that is the blood pressure indicated by the blue dots. So it's difficult to see, but they are blue dots. So we're only giving it that blood pressure and those volume flow rates. And the question is, can we discover what the pressure in the person's heart is? So that's indicated by the little red dots on that graph. So that is for a patient that has aortic stenosis. And the solid line that you see that's running through those dots was the discovered simulation results. So we could almost perfectly figure out, without invasively measuring directly the pressure, what the pressure was in the synthetic patient's left ventricle. We could also then do mitral regurgitation, so where your mitral valve doesn't want to fully close. So as your heart chamber pumps, not all the blood is going to your organs. Some of it's being pushed back in the opposite direction. And what we see there, the model can also accurately predict what the pressure in the ventricle is under those conditions. Now, hopefully, we've proved that this technique looks very, very positive and that most likely will give us very good results. The next step in this project is to actually deploy it on a sick patient. And hopefully one of my students, she is sitting in here somewhere, will take this further, one of my PhD students. And the one thing where the benefit of this project is compared to the projects that we find in literature is the current techniques, which is the finite difference method to find the gradient of the error between the measurements and the simulation outputs, is unable to accurately optimize the model and find the results. So by using deep learning or AI techniques like automatic differentiation and gradient-based optimization, we can drive the errors much lower and find those hidden parameters where it's not really possible with the current state-of-the-art techniques. Right, that brings me to the end, and I just want to say thank you to my students and colleagues for all their hard work and contributions, specifically to Prof. Peter Rousseau for being my mentor. When I started at UCT, he was the person that essentially taught me how to teach, taught me how to research. So thank you very much, Peter. I really appreciate all your help. To my family for all their support and the opportunities provided. To my wife for always being there, all the late nights, all the early mornings, waking up at 4 a.m. I'm still sitting in front of my computer. And then finally to my Savior, Lord Jesus Christ, for giving me the ability to do this research and also to teach my students and do it with passion and passion. Thank you very much for coming and listening. I really appreciate everyone for being here. So, I don't know, I think we are 5 minutes over time. So if there's 1 or 2 questions, I'm happy to answer them. I'm going to take 2 short questions. So hopefully from engineers. Yes?
How does the variability scale on that heart pump example you showed between patients? Is there any variability between heart chambers of different patients that you consider?
So the main parameters that would dictate differences in heart chambers would be the volume of the heart, so the relaxed volume of the left ventricle. And when we did the gradients through the model to determine what are the important parameters that affect the elastance of the heart, that was one of the parameters. So we optimized that as part of the solution. So we were trying to adjust also for size of heart. Elastance of heart is essentially the thickness of the heart muscle. So that is taken into account. Now, must be said that, remember, that's a model, not a real patient. So the real proof in the pudding is if we can model a real patient, not synthetic data, and replicate the changes that we see in a patient. But the positive note is those simulations, these lump parameter models, I'm not going to show it now, they have been proven to be a good replica of real patient cardiovascular biomechanics. Okay, I think if anyone has questions, we're going to have, thanks Prof. Moyo. Yes, so we've now published 4 or 5 papers with the cardiologists at Tygerberg Hospital, so the academics working there in cardiology, so Prof. Herbst and Dubel. So it's not that we're doing this on our own, don't know what we're doing, so we went to them, they came to us, so rather we went to them and they said, these are the problems that we need help with. So it wasn't that we figured this out. Yes, so the plan is actually to take this further, but I'm not working in biomedical anymore. I'm a little bit too busy with the thermofluids application. So this is the type of work that we did The first 2 years while I was when I came back to Stellenbosch from UCT, we did a little bit of biomedical work to get the cardiovascular biomechanics going at Stellenbosch. But I want to hand it over to one of my students. She's sitting there just behind you. She needs to take the work further. And of course, I'll help. But there's a lot of interest from the cardiology department. And I think, my opinion, it's just my opinion, I think in the next 10 years, the patient-specific treatment, the engineers will be very involved in those processes through simulation, data processing, machine learning. So I really think in the next 10 years, we're going to see a big shift in how patient treatment is performed. Okay, thank you very much.
Okay. No, it's fine. You can stand over
That
here.
side.
Yeah, because you spent a lot of time on this side. I think the people this side benefited.
My family was on that side.
On that side, yeah. Okay, so good evening, everyone. So my name is Sibu Moyo. I'm the DVC for Research, Innovation, and Postgraduate Studies at the university, and I'm grateful to just make a few remarks, a response from the rectorate. But before I do that, obviously to acknowledge all of you, and of course thank the faculty and the dean who has already done the protocols. So I'll observe all protocols with your permission so that I don't spend a lot of time on that. So just to say, as you know, so you've heard the lecture, and I just want then to congratulate our speaker for this lecture, and for, I've just lost my talk because it went somewhere. So I had used AI to try to do something while you were talking. Like, can you help me to summarize? But anyway, but that didn't work. But in any case, I just wanted to say that I acknowledge, of course, Professor Laubscher for the inaugural lecture, to congratulate you. As part of the university, we use these lectures, obviously, to communicate what the professor in that field has been doing to fellow colleagues, but also to the public. And I think it's so important to to be able to explain what one is doing so that people can understand. And so, yeah, so tonight we have experience, of course, this just from your lecture. And then, of course, the lecture was on harnessing deep learning for thermofluid systems. And being a mathematician myself, I really enjoyed it. I saw some equations, but of course they were, they were in the corner somewhere, but now they make a lot of sense, of course, seeing the applications from the engineering side. So in this lecture, I think what is important for me is to see how the theoretical work, the computational side, and also using the deep learning and artificial intelligence, how that can help us to understand. And I think that's important to just note. But then also I think the optimization, so in mathematics we work, when you're doing differential equations, optimization and maximization of systems, whatever systems you're looking at. It's important to see, I think we do that from the theoretical side, but I think to have data, the power of data and the power of seeing what that means in real life is so important, and I think that's a big takeaway. I wanted to ask you a question, but I didn't get a chance. You talked about a company you didn't want to mention. I assume that the work you've done has contributed to this company making a lot of profit, because on the energy side, for the first time, there's been a big profit declared by one of the companies, but I won't force you to ask in case you are funded by them. So I thought that was really great. I was a bit shocked because I thought they're charging us quite a bit, but never mind. So allow me at this juncture maybe to just say a few things. So I'll not go into the summary of what he has said, because I think it's very clear, and also he shared very well, but I think what's important to say is that when you think about inaugural lectures, for us, just the way you have shown, from the foundational studies that are done within this field to the industry-based applications, but also you talked about the health applications, and I think it's good to see also the potential translation into, of course, patient outcomes, but I guess on the engineering side, it's other applications which one can consider. And then also on behalf of the university, maybe I must just say that for us, these lectures also signify an opportunity for the university to make impact in terms of our research. So having research which can be translated into possible solutions is also a key aspect, and to do that, from the theoretical side to the application side, showing that also makes a big difference. And then the other thing I think which is really key from today is also to see the way you bring in the students. So if I can just check in this group, how many of you are students? His students? Okay, wow, that's quite a lot, yeah? So you're already making bigger impact. And I want to congratulate you for that as well. And I think it's a big, many students I know, do you guys love engineering? You love it with passion. And how many ladies, can I see lady students, engineers? Raise your hands high. Good. At least we've got some future engineers, because we always talk about also the interest, yeah, in engineering, which we try to get. I tried to force my daughter to do engineering. I was not successful. I think she did mechanical engineering, but she's gone into data science, so which has been quite interesting as well. So yeah, so I think to see, one of the successes of a good professor is also the ability to teach others, the ability to be able to mentor others, and we've seen that. So it's a combination of that. And I think also the fact that you've spent time in industry, that you've been in academia also gives, a great sort of advantage in terms of the application side. Because most of us spend a lot of time in the classroom without really being in the industry side. So that also may limit, one's exposure in terms of what's happening in the real world. So I want to congratulate you, of course, on behalf of the university in terms of that as well. So having said that, I have the honor then to present you with a certificate to prove that this certificate is a symbol from the university to just show that you have given the lecture, and also to congratulate you on your promotion to full professorship, and also to congratulate the department. Who are the department members? Just raise your hand from the department. Yeah, to congratulate the department, because it takes everyone to contribute, and the faculty as well for the successful lecture that you have given. So yeah, so this is for you. Please, can you clap for him again? Yes, can I call, so you may sit, and then we have the next colleague to just give the remarks. Oh, sorry, I left my key document.
Yes, I can use it.
Oh yeah, you're welcome to use it. But
Thanks, colleagues. I think of the story of Jan Spies van baie dankie. So you have to always end with saying thanks. So those of you that don't know the story, do yourself a favor. It's good reading. So it's very nice seeing all of you here. I have the honor to do the last part of the ceremony. So I just have to thank a few people. So first of all, the staff from the Corporate Communications Marketing Division for all the arrangements, the recording, the live streaming. I hope everyone is still online. Thank you very much, Amira, Chuma, Krista, Justin, and Jonathan Dale Blankenberg. Jonathan is the one that keeps chasing us to make sure that we do submit our presentations and our papers and everything in time. Then also to the rectorate, so our DVC Research, Innovation and Postgrad Studies, Prof. Sibu Moyo. Prof. Moyo, you're always welcome. It's always nice seeing you, and we always appreciate the effort you make. I'm quite upset about your daughter, but I understand. Then from the faculty, Prof. Aniker is Dean, thank you very much, and then also Prof. Cornelis Skutte, Vice Dean Research and Industry Liaison. Thank you also for us as department, the support that we get from your side. Then our honorary speaker, Prof. Ryno Laubscher. Ryno, baie dankie. Ons waardeer jou. Jy maak 'n wonderlike bydrae. Is baie lekker om jou in die departement te hê. It's very nice having you in the department. I always enjoy the discussions. It's not always about academics. Always also about other interesting things, but nevertheless, baie dankie, Ryno. It was a very good presentation, by the way. Then the Dean's office staff, specifically Ulrich, Clinton, and Jamie, to make sure that everything is set up and organized and ready for this. And then finally also, and I think she's left the building, is Marily. So this morning when I was wondering about where I'm going to get the list of names to thank everyone, the email just magically appeared from Marily. Marily, baie dankie. Always reliable. If you don't know anything, you just ask Marily. She can organize anything for you. And then finally, I invite you all to come and enjoy some refreshments with us, and we're going to ask Ryno some more questions if you'd like. Thank you very much.
Thank you, Prof. May you all please rise as the procession leaves the venue.